In this video, we will have a detailed look on solid solution. So we have seen that solid solution is a type of alloy. It is a type of uh, alloy, and in this you can see that the first point is that in solid solution, the variation in composition is possible. Variation in composition is possible. We have seen some examples like copper nickel alloy. Okay, in copper nickel alloy, you can have any combination of copper and nickel, but in some other alloys, it is not possible. We will see why it is like that. But we have also seen another type of alloy that is called intermetallic compounds. Okay, intermetallic compound. That is another type of alloy. In this, you can see that the variation composition not possible. That is, it has got a fixed composition. Okay, it has got a fixed composition. One more thing you need to keep in mind in solid solution is that the crystal structure of the alloy, crystal structure of alloy is same as that of one of the components. One of components. Crystal structure means if one is FCC and another is BCC, then the resulting alloy may have a crystal structure of either BCC or FCC. Will not have a crystal structure other than that of FCC and BCC. That is what this says. Okay, let us look at some um, common examples of a solid solution. Like first, let us look at in steel. You have two solid solution. The first one is austenite. This one is austenite, and then you have ferrite. Okay, then you have ferrite. Okay, so this is a solid solution of carbon in gamma ion or FCC ion. This ion exists in two phases. One is FCC structure and other is the alpha ion which has got a BCC structure. So ferrite is a solid solution of copper, that is FCC and zinc. And sorry, so a solid solution of carbon in alpha ion or BCC ion. Okay, then you have another example here is alpha brass. That is a solid solution of copper, that is FCC and zinc, zinc HCl. And resulting alpha brass has got an FCC structure. Okay, it has got the structure of copper here. And we have also seen what are the different types of solid solution. What are the different types of solid solution? So let us look at that. That first one is the interstitial solid solution. In- Interstitial solid solution. And then you have the substitutional solid solution. Okay. We have seen in the previous lecture what is interstitial and substitutional solid solution. We will discuss in detail here. Okay, first let us take the case of interstitial solid solid solution. Taking interstitial solid solution. Um, let us draw. So these are the okay. Let us take the example of austenite or steel. You have these iron atoms here, and, and these are called generally we will call these as solvent atoms. And here you can have these are the solute atoms. Okay, these are the solute atoms. Okay. So the solute atoms occupies the interstitial positions of the solvent atom. So that is what you mean by an interstitial solid solution. So the solute atoms uh, sits in the voids of solvent atoms. Solvent atoms. And in one example we have seen that is austenite. Example is austenite. That is carbon in voids of cubic close-packed structure iron. Next, you have the substitutional solid solution. That is the substitutional solid solution. We have also discussed about that. In this case, you have the solvent atoms like this. Here, the solvent atoms is completely one solvent atom is completely replaced by another solute atom. This is so here this is the solute and this is the solvent. This is the solute and this is the solvent. So this is what happens in a substitutional solid solution. And here you can see that the radius of the solute atom is comparable to that of the radius of the solvent atom. In interstitial solid solution, we need to keep in mind that the radius of the solute atom will be very much less than that of the radius of the solvent atoms. There is the difference in both these solutions. Okay, in this video, we will mainly focus upon the solid solubility limit or the Hume-Rothery rules. That is the solid solubility limit. Solid solubility limit. First, we will discuss about solid solubility limit, and then we will discuss about the Hume-Rothery rules. That means we are discussing about the what is the maximum amount of solute atoms that can be present in a solvent in a alloy. Okay, it's in an alloy, or so here the alloy is a solid solution. Okay, how will you find that? So it is not an intermetallic compound. So the percentage of the either component is not fixed. It can vary. We have seen that the composition can vary. So while checking the solubility limit, we have seen that like Example, let us take the austenite, that is the gamma austenate ion, that is carbon in gamma ion, that is austenite, an, has got an upper limit of solubility. That means you cannot add more than 2% of carbon to ion. And another example is the copper zinc alloy, that is alpha brass. This has got also got an upper limit. You cannot have a you cannot go beyond a limit. Okay, we will see why. It cannot be mixed in any proportion. But some examples like copper nickel. Okay, this copper nickel forms or a this is a substitutional solid solution. This is a substitutional solid solution. This is a substitutional solid solution, and this can be mixed in any proportion. This can be mixed in any proportion. That is the difference. So why is it so? Okay, to understand that, we need to know the Hume-Rothery rules. Okay, that is where these rules come to understand about to define the solubility limit. Okay. So once we understand the Hume-Rothery rule, we can predict the solubility limit also. So first, let us take the example of the interstitial solid solution and see why it has got an upper limit. So first, let us take the pure metal A. This is a cartoon picture. Okay, that is pure A. And so when you alloy it, that is when you add the solute atom to the interstitial solid solution, see, so this is a solid solution. So you can see, you can have a solid solution up to like this. See, you can fill all the voids. Okay, here I have filled all the voids. So this one was here in the second picture, it was partially filled. So here you can see that it is all the voids are filled. All the voids are filled. So from this picture, you can see that there is a geometrical limit. There is a geometrical limit to this limit of solubility. That means you can fill only up all the voids. Beyond that, you cannot go. So that means unlimited solubility is not possible. Solubility is not possible. You can fill only the voids only. Okay, after all the voids are filled, you cannot add any more atoms. Okay, now let us look at an example that is austenite. So this example we have seen earlier, that is austenite. That means carbon in gamma ion. Okay, that's UCC ion. Okay, so here the carbon here goes to the octahedral void of this gamma ion. Okay, this gamma ion, it has got an FCC structure, and this structure has got a void. That means the area where the ion atoms are not present, that is called a void, and it is called an octahedral void. So the carbon atoms can fit into this octahedral void. And if you look at the geometry in an FCC structure or cubic closed pack structure, you can find that there is one octahedral void per atom. Okay. For every one atom in a face-centered cubic structure, you have one octahedral void. Okay. If you look at that, what will be the geometrical limit? What will be the geometrical limit if you go like this? That means one carbon atoms for every one iron atom, you have one carbon atom per one iron atom. So that means the geometrical limit is uh, 50 percentage, 50 atom percentage of carbon in iron. But the maximum solubility limit we have seen, maximum solubility limit we have seen is only 4 percentage for weight percentage carbon in iron. So this is weight percentage. That means carbon has got an atomic mass of 12 and iron has got an atomic mass of 56. So that means if you compare that to the uh, atom level, that means the ratio of the mass is almost somewhat equal to 4. That means it will be 16 atom percentage of carbon in 16 atom percentage of carbon. So that means for 100 atoms of iron, you will have 16 atoms of carbon. So that is the difference. So, but the geometrical limit we have seen it is 50. Okay? And for every 100 iron atom, you can have up to 50. So this is the uh, geometrical limit. This is the geometrical limit, and this one is the uh, real limit. Okay, real limit that uh, we are seeing. So why is it so? Why we cannot achieve the geometrical limit? So let us see why is it so. So for that, I told you that this carbon atom occupies the octahedral fold. So what is this octahedral? What is the size of this octahedral fold? The size, the radius of the octahedral void can be derived from the cubic structure. So this is actually equal to root 2 minus 1. So this is given as a statement. This can be derived. Uh, so this is root 2 minus 1 into radius of the iron atom. So this is equal to 0.414 radius of the iron atom. But the radius of the carbon atom is greater than the octahedral volt. So this causes a misfit, which displacement, causes displacement of surrounding atoms, displacement of the surrounding atoms, which causes a strain in the matrix, causes a strain in the matrix. So this defines the limit of solubility for an interstitial solid solution. In next video, we will look at the actual Hume-Rothery rules. That means we will discuss about the solubility limit in a substitutional solid solution.